Hello, my name is Charles Jarbo, and I'm a research scientist at the Light and Health Research Center. In this video, we will cover designing for circadian stimulus. In this video, we will discuss the use of software tools for designing for circadian stimulus, how to incorporate daylight into your design, how to interpret the results of your calculations, iterative design strategies for when at first you don't succeed, how to try again and hopefully do better, and then steps for design verification. So first, I'm going to cover the usage of software tools. Photometrically realistic software is critical for lighting design, specification, and evaluation. There are a variety of software programs available on the market, and it's not key that you use any one of these in particular. However, there are some key features which this software should provide for the results to be the most accurate. The first is that the user should be able to define photometrically accurate luminaire definitions, usually in the form of IES files that include the total lumen output of the fixture, the intensity distribution, and allow the user to define light loss factors as they see fit. Additionally, the user should have the ability to define not only horizontal illuminance calculation points in the model, but vertical calculation points as well in the plane of the eye of occupants in the space. And this is because CS is dependent on light reaching the eye of occupants. And finally, the software should utilize the full radiosity method for the most accurate photometric results possible. So the first steps to utilize in the photometric software when designing for CS is to define the vertical illuminance or EV calculation points in the model and place those points at roughly eye height for a seated occupant, assuming they will be seated at furniture, roughly 0.9 to 1.3 meters above the finished floor, and to aim those points in the direction of the occupant's gaze throughout the space. So when the furniture locations are known, the designer or specifier should put the EV calculation points at those locations and try to utilize at least 10 locations throughout the space to get a good understanding of how much CS occupants of the space will get no matter where they may be seated or what direction they may be looking in. However, when the furniture locations are unknown or are changeable, it's important to quantify on average throughout the space how much CS an occupant may get by placing vertical illuminance calculation point grids throughout the space aimed in the 4 cardinal directions. It's also important to utilize layers of light, just like you would in lighting design itself. Within your photometric software, it's important to define and treat your layers of light separately and get creative and try thinking outside the ceiling plane. It's important to calculate the EV contributions or vertical illuminance levels from these layers of light separately because CS is not an additive function. It's not enough simply to know how much CS you're getting from one layer or another and then add those two together. You need to combine the spectra of your sources and your layers of light within the CS calculator and then calculate CS. And I'll go over that in more detail in the next slide. And it's also important to build scenes in your photometric software, particularly when you have different CS targets at different times of day, to understand how much you'll have to dim the various layers of light and how they'll combine together. And this is all especially true when you have multiple spectra, different light sources emitting different color of light combining together, like if you're using white light combining with blue as shown in the example here. So when your photometric calculations are complete, the next step is to utilize the LHRC's web-based circadian stimulus calculator. We cover in far more detail how to use this calculator in video 6, so if you need more information on how to use the calculator and interpret those results, please take a look at that video, if you have not already. But in general terms, the first step is to input the light source SPD or spectral power distribution values, to input your EV calculations for your various layers of light, and then to calculate the CS utilizing this tool. Next, I'll cover the incorporation of daylight into your design. Daylight is a key component of green building design and has been for a very long time. Benefits of daylight include energy savings from the reduction of electric lighting energy required in your design, a connection with the outdoors by way of views through glazing to connect people with nature and weather conditions outside. And of course, circadian stimulation from daylight. Daylight has a very effective spectral power distribution for stimulating the circadian system, and when delivered into the space in the right amounts can be in a very effective way to deliver CS in your space. So it's very important to consider daylight design very early on in the architectural planning and design process. And this is to ensure that glazing is utilized appropriately and to avoid certain pitfalls, such as excessive heat gain or loss in your space, which can counteract energy savings from reducing lighting energy requirements. Direct sunlight in the space can cause glare and should be avoided when possible. And it's also important to make sure that the daylight coming into the space is uniform and is utilized well to avoid underlit areas that aren't benefiting as much from the daylight, and to plan your interior spaces and furniture layouts to best utilize daylight as much as possible. So when it comes to modeling and performing daylighting calculations in your photometric software, it's important to model the glazing in your software and understand the transmittance of the glass itself or whatever material is transmitting the daylight from outside to inside your space. You want to perform a daylighting study, which involves looking at not only geographic factors surrounding buildings and trees that might block sunlight coming into your space, but also look at the effect of time of year, the time of day, as well as the sky conditions, as all these variables can affect how much daylight you will get in your space, and to then assess the worst case scenarios as shown in the red box on the lower right corner of the screen here. This analysis was done for a site in Stockholm, Sweden, and the red box is surrounding December, so the winter time with a cloudy sky. And as you can see, the illuminance values in lux for the 8 vertical calculation points or locations in this model are showing little to no illuminance from daylight at all. So obviously this is relatively intuitive that during the winter in Sweden, you're not going to get a whole lot of light in your space from daylight. But it's also true that even during the summertime, for certain seating locations in the space, the daylight levels are still quite low, even in the summertime and even on a clear day. So it's important to understand this, to model this, and to know that the electric lighting is going to have to do most of the work when it comes to delivering circadian stimulus in your design, because there are challenges associated with utilizing and relying on daylight. Some additional uncertainties related to daylight include the position of the occupant and how the furniture is arranged, the direction that the occupant is looking, including the angle of gaze, whether they're looking down at their desk, and of course the positioning of blinds and or shades. In the image shown on the right here, this occupant of the space is seated very close to a window. However, their direction of gaze and the fact that they have the blinds closed are probably reducing the amount of light they're getting at the eye quite dramatically compared to if they were looking out the window, for instance. So the next step is to treat daylight as another layer of light in your calculations and in your space. Calculate the EV contribution from the daylight in isolation, and you can do this by utilizing the preloaded CIE standard daylight SPDs that we have in the calculator, and then combine the layers of light as needed, including your electric light, to calculate the total CS values in your space. So next is how to interpret your results, and what does the workflow for this process look like in a nutshell. Basically, it starts with your photometric simulation, and then the data from your calculations should then be exported, copied, pasted, somehow saved into a centralized data management software. Something like Microsoft Excel is a good option, because from there, your photometric illuminance calculation values will then be put into the CS calculator to perform the CS calculations. And then you have this feedback where then the CS results go back into your spreadsheet, and you can look and see whether or not these values are actually meeting your targets at your various times of day based on your CS schedule. And then from that information, there will be feedback into the photometric model where you can make adjustments as needed. So that gets us into the iterative design strategies. The CS targets are unlikely to be met on the very first try, to be frank. It's a difficult and somewhat complicated process. It involves a lot of variables to be concerned about, so chances are good that some things will need to be adjusted to hit your CS targets, particularly for daytime occupants, when these CS values need to be high. So one place to start is to adjust luminaire spacing as needed to increase EV at the furniture locations. Try a wide intensity distribution from your light source or direct, indirect light sources that can increase the amount of light at the eye, EV, to the amount of light that you're getting on the work plane. And aim for an EV to EH ratio of around 0.6 to 1. And this explains how efficiently your light source is delivering light at the eye relative to how much light on the work plane you're getting. And you obviously want to aim for more light at the eye, but still to avoid glare, make sure that this ratio is not excessively high or that you're getting an excessive amount of light at the eye at high angles. It's also important to adjust the luminaire lumen output or to look at different light spectral power distributions. If you can't increase your light levels for some reason, whether that's energy or illuminance level limits that you may have in your design, it will be important to look at more efficient spectra for getting the job done. Additionally, and critically, it's important to think about additional layers of light, as I noted before. And you can use layers of light geared solely towards the efficient delivery of daytime CS. And this can include eye-level lighting, so lighting in the vertical plane close to the eye of occupants, illuminating vertical surfaces, and utilizing saturated blue light to very effectively deliver CS for not a high additional amount of energy. So lastly, in the design stage, it's important to produce documentation that project managers can utilize to verify that the design is meeting the targets. So this generally includes the CS schedule, which lays out what the CS target values are at your various times of day. Show the detailed luminaire and light source specifications. This is key to project managers being able to see what you're proposing to use in terms of the fixtures themselves. Obviously, you need to provide the photometric calculations in some form of a report that show not only layouts, but also tabulated data showing the values that you got in your calculations. So this should also include at least one elevation view in addition to plan views, because the elevation will show the calculation point heights and aiming angles as well as the values at those various locations throughout your space. It's important to list the assumptions you made in your design. These generally relate to the reflectance values of the various surfaces and objects in your space, as well as what assumptions were made about the daylight parameters. If that assessment was performed and you did a daylight analysis, it's important to list the assumptions made for that. And then finally, you want to show the results of the CS calculations. Usually in a tabulated format is best, showing the CS targets, the values for the EV and EH, and then the calculated CS values for at least those 10 locations throughout your space. So I hope you've enjoyed this video about designing for circadian stimulation. Thank you very much.